going to start with the free response questions from the last test. We'll go over those, and then I'm going to work a Hess's law problem because I've had a lot of questions about Hess's law. And then I'm just going to talk about some general mistakes that I saw on the multiple choice. So the first question is about aluminum, and there are two ways that they're describing that you can get aluminum. You can just melt aluminum and get rid of the impurities, and that takes a certain amount of energy, melting it. Or you can use this reaction that they give you and you can produce aluminum. That is an endothermic reaction, so it also requires energy, and you're supposed to figure out basically which one takes more. So the first part, the melting of aluminum, we know that anytime you melt a solid, you have to go from solid to liquid, or solid to the melting point. That's a temperature change. And then once you've changed your temperature and you're at the melting point, you have to melt it. And remember, there's no temperature change when we're phase changing. Okay, so for the first part, the trickiest part of this question I think was that they didn't give you grams, they gave you a mole, but they gave you your specific heat and enthalpy values in moles, so you didn't have to do anything with it. So you have 1 mole of aluminum times the molar heat capacity, which is the specific heat capacity just in moles, which is 24 joules per mole Kelvin. And then the temperature change, you're taking solid aluminum to the melting point. So you're going from room temperature, which is 298 Kelvin, to 933. 933 minus 298 is 635 Kelvin. When you multiply those, you get 15,240, or 15.2 kilojoules of energy. And that's the energy required to change the temperature of the solid aluminum from room temperature to the melting point. Once we're at the melting point, we're going to take our 1 mole and melt it with the molar enthalpy of fusion, which is 10.7 kilojoules per mole. And that whole thing takes 25.9 kilojoules. You just add them up. Energy to change the temperature, energy to melt. Questions or comments on that? Okay. The second part, we have this reaction. Aluminum oxide goes to aluminum and oxygen. It's basically the reverse of the combustion of aluminum. And that is an extremely endothermic reaction that requires 1,675 kilojoules per mole. And the question is, the equation for the process of extracting aluminum is shown below. Which requires less energy, recycling or this? And it says, justify your answer with a calculation. So this produces 2 moles of aluminum. That produced 1 mole of aluminum. So the calculation was divide by 2. And this requires 837.5 kilojoules of energy. And then the question, which requires less? Recycling. A lot less. And that's it. Questions? Okay. The next part, wanted you to draw a Lewis diagram for ozone. So O3, you have 3 times 6, 18 electrons. O, you have 14 left. And then because there's a double bond, you have to include resonance. Questions on that? Okay. The next part is, B. Based on the diagram you drew in part A, what is the shape of the ozone molecule? 1 lone pair and 2 atoms bonded. What shape is that? Bent. Right? 1 lone pair, 2 things bonded. Bent. Okay, then part C is admittedly tricky. So I'm going to erase this so I have room. Part C says the bond enthalpy of the oxygen-oxygen bond in O2 is 498 kilojoules per mole. Based on the enthalpy of the reaction above, what is the average bond enthalpy in kilojoules per mole of an oxygen-oxygen bond in O3? So the reaction looks like this. And the enthalpy of that is negative 285. And then they tell us the bond enthalpy is 498. Okay, so what we're doing, we have three of those being formed, right? I didn't include lone pairs, but we have 3 of those bonds, types of bonds being formed. And each one that gets formed releases 495 kilojoules of energy times 3. And it's positive because making bonds is exothermic. Releases energy. And the bonds we're breaking are these. Right? And it doesn't tell us to specify between an OO double bond in that or an OO single bond in that. It just wants us to find, based on the enthalpy of a reaction, what is the average bond enthalpy of an oxygen-oxygen bond in O3? So all we're saying is each of those is the same, because remember they're averages. So they're X, and there are 4 of them. And sorry, this would be negative because it's released. This is positive. And then the sum, so 4X minus 495 times 3 has to equal the total energy for the whole reaction, which is negative 285. And then you just solve for X. So,
Where did you get the 4 from?
because there are 4 of them that all need broken. And we're assuming that they're the same because they're average. We're finding an average. So,
Why do all of them need to be broken? Couldn't you keep the double bonds intact and just break off the O's that are single bonded and bond those together?
You could, but that would give you the same enthalpy, but we're just trying to find what is the average enthalpy in those.
Okay, so it doesn't technically matter.
Right,
Okay.
but that wouldn't answer the question.
Oh, yeah.
Okay, so it's 300. I don't think that's right. Because this is supposed to be 498. My bad. Okay. 498 times 3 minus 285. So those bonds are roughly 302 kilojoules per mole for the bond enthalpy. Okay? The next part is the kinetics part. The data are consistent with the following rate law, K equals O3, or rate equals KO3. Based on the graph on the previous page, which it's not, determine the half-life of the reaction. So we go from 1 times 10 to the negative fifth to 5 times 10 to the negative fifth in 0.01 seconds. And then we go to 2.5 and another 0.01 seconds. So the half-life is 0.01 seconds. The second part, determine the value of the rate constant K. Include units with your answer. So you can choose any data point. It doesn't matter. Wait. Did I give you anything other information? Okay, so you would have to use the half-life equation, which is T1/2 equals 0.693 over K, right? So 0.01 equals 0.693 over K. Gives you 69.3. And it would be reciprocal seconds. The next part, considering the relative concentrations of the reactants, briefly explain why the data in the graph are also consistent with the following rate law. Rate equals KO3 HSO3. Why? K2, sorry. Why does that work as well? No? That would be a second order reaction, right? Not a first order reaction. But one of them must have a very low concentration in order for that to work. And then the last one, briefly describe an experiment that could provide evidence to support the rate law given in part DII. You would just have to monitor the HSO3 and the O3 at the same time and get data like we always have and see how that data affects rate. Okay, that's it for the FRQ. Let me go back. trying to find one that I haven't worked, but I think. I'm going to do number 3 on the Hess's law. Calculate the standard enthalpy of formation of benzene. So benzene, we're trying to find the enthalpy of formation, which would be 6 C's plus 3 H2's makes benzene. That's our goal, given the standard enthalpies of combustion. So C6H6 plus O2 makes CO2 and water. The combustion of that is negative 3270. And it needs balanced 6 carbons, 6 hydrogens. 12 plus 3 is 15. So this would be 15 halves of an O2. The combustion of carbon is negative 393.5. And the combustion of hydrogen is negative 285. Okay. So those of you who are struggling with Hess's law, if you are given an enthalpy of formation, that's this. This is enthalpy of formation. You make one of those things from its base, diatomic or elements. If you're given an enthalpy of combustion, take that thing plus oxygen to produce whatever makes sense. That oxide or carbon dioxide and water. That's really it. Those are the only 2 types of things we use to do Hess's law. Once you have your reactions written and balanced, enthalpies of combustion, you always combust one of those things. Never change this coefficient. Enthalpies of formation, you always form one of these things. Never change this coefficient. Then, once you're here, you start manipulating them to make things cancel that aren't here, or to get as many of these things as you need. So, I need 6 carbons as reactants. Multiply this by 6. I need 3 hydrogens as reactants. Multiply this times 3. And I need C6H6 to be a product. So I'm going to flip this whole thing to be 6 CO2s plus 3 H2Os. And 15 halves of an oxygen I'm going to write as 7.5 oxygens to make it simpler. And if I flip that, I just need to flip the sign here. Something's wrong. Can I not do math? Oh, this is 3 halves, not 3. Oh, wait, no. That's 3.
No, it'd be 3 halves because you have.
It should have been a half before. You're right. Thank you. Okay, 3 halves. Okay, at this point, we cancel things to cancel. Carbon dioxides, we have 6 and 6. Waters, we have 3 and 3. Oxygen, we have 6 plus 1.5 is 7.5 and 7.5. And then we have 6 carbons plus 3 hydrogens makes C6H6. That was my goal. So then I just add these things up, and that's my answer. It's always easier when you watch me do it. I know that. All of these problems, I feel like you all could do it if I said, just start here. Start with this. You could totally do the rest of the problem. That's the hardest part of all of this. The multiple choice. I saw you all struggling when the question was really just a sig-fig question. Or it was really just an endothermic, exothermic type of thing. Don't waste time doing math you don't need to do. Analyze your choices before you start trying to do math. Most of the time, there's not math necessary. The choices narrow it down for you. Tomorrow's test will be multiple choice and free response all in one test. You'll open it up, you'll encounter some multiple choice questions, and then there will be some free response questions. You'll answer it all on there and submit it. I've decided that if your grade on this test does not appear to be significantly better than your other test, I'll go back and check and make sure you've actually improved, and I won't punish you if you did worse this time. I don't anticipate anybody doing worse on this test, but it could happen. I do, no matter what, even if you think, oh, my first test was fine, I want everybody to do it. It's all you're doing tomorrow. It's open book, open note. You'll have 45 minutes. It's open book, open note because some of you will be at school and some of you will be at home, and I can't control it. So everybody gets to use books and notes. Really just notes because your book is whatever. All right, that's it.